Alright, 1-5. We're going to review solving inequalities. I guess to be more specific, one variable inequalities. So, question to start things off. How many solutions are there to the equation 2x plus 3 equals 5? Remembering what it means to be a solution and that this is an equation, that's something important about it. There is how many solutions? One solution. There's one solution, and if you were to work the equation and alter it and so that you end up with x all by itself, you would be able to see what that one solution is. As I do this in my head, I believe the solution is 1, that x equals 1 is the... don't be confused by that. There's one solution, and it's 1. The next question, how many solutions are there to the inequality 2x plus 3 is greater than 5? How many numbers are there that you could replace the x variable with to make 2 times x plus 3 greater than 5? And hopefully you kind of, from your experience and just, you know, natural understanding and intelligence here and knowledge of numbers, that there's infinitely many numbers that we could plug in for x to make 2x plus 3 actually greater than 5. Let's come up with 5 of those solutions. Just 5 examples of numbers that would solve and satisfy this inequality. And let's just cut to the chase. Did I give 5 here? 1, 2, 3, 4, 5. Looks like I gave 6. Or wait a minute. What is this? What the heck? 85.5. Maybe I did give... What the heck? Sorry. Maybe I did give 5. So 2 is a solution, 5 is a solution, 10 is a solution, 85.5 is a solution, 1,000 is a solution, and obviously there's plenty more. There's infinitely many more. But if you plugged in 2, like 2 times 2 plus 3, that's bigger than 5. 2 times 5 plus 3, that's greater than 5. 2 times 10 plus 3, 2 times 85.5 plus 3, 2 times 1,000 plus 3, all kinds of numbers that are solutions. And if we represented the solutions on a number line, how would we do that? Right? I mean, and look at this right here. Is 1 a solution? Like if we plugged in 1, because remember, when we plug in 1 to the equation, it makes it true, but is 2 times 1 plus 3 greater than 5? If we plug in 1 for x, we're going to end up with an inequality that says 5 is greater than 5. That's not true. And so 1 is, that's a no. It's not a solution. So we can't graph that, but I mean, so I guess here's what I'm getting at. What is the smallest, what's the smallest solution? Is it 2? Because apparently there's no limit. There's to like how big the solutions can get, 85.5, 1,000, 1,000,000. I mean, doesn't seem to be any, limit on how big this. But what's the smallest solution? Is it 2? is there any number smaller than 2 that you could plug in here and make this true? Or smaller than 2? Maybe I misspoke there. Is there any number smaller than 2? What about like 1.5? Would 1.5? So I'm gonna put like I'm gonna put a 1 right here, and we'll call that 0, and that makes that -1. So 2, 3, 4, 5. So it looks like we're going to be, this counts, and 3 counts, and 4 counts, and we're going to be like shading in all of the answers. But again, like 10 and 85.5. So right there, it's like, is 2.5 a solution? Yeah. And so there's all kinds of points that we just need to basically color in, and it goes off to the right forever. But like we said, what about like 1.5? What about 1.01? Like, is that a solution? Yeah, and it's like, so what's the smallest solution? 1.0001? No, because we could say 1.00000001 is a solution. Hopefully you see where I'm going with this. So here's how we actually draw the graph, the picture of all the solutions. We can't really say what the smallest solution is. We just know that it doesn't include 1. And so we draw an open circle, like an open point on 1, and we just kind of shade everything to the right of 1, So as it turns out, like if we were to actually solve this, which you're probably going like, let's get to the point, like we already know how to do this. And if you solved this for x, you would end up with x is greater than 1. And that's how you draw the number line graph of x is greater than 1. Strictly greater than 1, not also equal to 1. That's why we have an open circle right here. So again, finally, let's get to the point. We're going to be solving for x, as you probably already know, the same way we would solve for x if it was an equation. And so here our first move is going to be distribute to clear the bubble. So 3 times 2x is 6x. 3 times -5 is -15. Bring down the +1. And so now, and the left side is just 4. So 4 is greater than or equal to 6x minus 15 plus 1. As you should know, the next sort of priority is to combine any like terms that are already on the same side together, like -15 plus 1. -15 plus 1 is -14. And now we're going to look to get the x all by itself on one side. And so I'm going to add the 14 over there. And so that leaves 6x over here. And now the left side is 18, which leads to dividing both sides by 6. And so this becomes 3 is greater than or equal to x. 3 is greater than or equal to x. I'm going to highly, highly, highly recommend that you kind of flip all this around and just kind of read this more from right to left, Saying that 3 is greater than or equal to x is identical to saying x is less than or equal to 3. It's just like saying, if 4 is less than 7, if you were just going to re-say that the other way, you would say that 7 is greater than 4, but you don't. Just kind of elaborating there. And the directions want you to graph the solution, if you don't have a number line already, you can draw your own and just say, well, let's just say 3 and, everything. So we want to shade in everything less than or equal to 3. So everything less than 3 is to the left. And since we can be less than or equal to, we're also going to color in the circle on 3, because now 3 counts as a solution, not just everything less than 3, but also everything that's equal to 3, shade in 3. At least one more example here. What would you do first to solve for x? Wouldn't you need to subtract 3 from both sides, which still leaves a negative 4x on the left side, and the right side would now be 8. And now we're going to have to divide both sides by a negative 4, which isolates the x. 8 divided by negative 4 is negative 2, but do you remember from your past training that whenever you are solving an inequality for x, and along the way to getting x by itself, if you end up multiplying both sides by a negative number or dividing both sides by a negative number, like we did here, we divided both sides by a negative 4, you have to flip the inequality symbol. So less than or equal to becomes greater than or equal to. And now that means our final graph, is going to be greater than or equal to negative 2. Okay? And this activity right here, it's almost like these notes are a little bit out of order, but this quick activity right here just kind of shows you, like a pretty good look at why we do that. I mean, just look at how numbers act with greater thans and less thans, and when you just work with negatives, it's just the way it goes, So let's say you started with 4 is less than 6. If you multiplied both sides by 2, 8 is still less than 12. Like, this inequality is still true. But if you multiply both sides by a negative 2, you have negative 8 is less than negative 12. Is that still true? No, and that's just the way numbers work with negatives and being less than or greater than something else, right? It's just the way it goes. If you were to divide both sides of 4 less than 6 by 2, you'd still have something that's true. But if you divided both sides by negative 2, this guy, you'd end up with negative 2 is less than negative 3. And again, that's just not true anymore. And to make it true, you'd have to flip the less than to a greater than. Just like here, to make this true, you'd have to flip the less than to a greater than. And again, I'm just kind of repeating what I just said on the last example. But if you multiply or divide both sides of an inequality by a negative number, you must flip the inequality symbol. Feel free to pause the video. You probably will need more time to write all that down. I'm moving on. If you need to pause and then unpause, whatever. So here's the next example. Let's see what happens as we solve this for x. Of course, starting off with distributive property to clear the bubble. 5 times 2x is 10x. 5 times minus 3 is minus 15, and then bring down the minus 7x, and basically bring down the rest of it. I see some like terms on the left, 10x and negative 7x. That's going to be 3x, and the minus 15 is still as is, and the less than 3x plus 8. And now we we're pretty much at a point where we need to get the x's, the x terms, only on one side. So let's subtract 3x from both sides, and oh, wait a minute. That leaves 8 over there, but 3x minus 3x, that's also canceled out. Like, that's 0x, just like over here. Basically, it's gone. So, wait. Do you remember from previous math classes how this can happen? The variable can totally cancel out as you work on, isolating it on one side. Like here, we're just left with negative 15 is less than 8. And when this happens, okay, your variable totally cancels out as you try to solve. What you're left with is either completely, totally, always true or false. So basically, is negative 15 less than 8? Like, is that true or is that false? And as it happens, negative 15 is, in fact, truly less than 8. So what this means is that the inequality is always true. And another way you can finish off this problem is that that there is an infinite number of solutions. Infinitely many solutions. Essentially, no matter what you plug in for x, an infinite number of solutions, no matter what you plug in for x, any number would make this true. So that's basically the solution to this example, this inequality, that all real numbers are solutions, and there's an infinite number of solutions, because of that, basically, and that this inequality is always true. Now we're sort of taking it up a notch, and we're going to talk about these things called compound inequalities. And this shouldn't be new to you either, really. Compound inequalities just kind of means that there's two inequalities going on at one time, and they're either going to be connected by the word and or the word or. And those two words have very specific meaning and very specific implications, just like they do in the real world, right? If you were starting a club, like a social club kind of deal, right? A very exclusive club. And let's say in order to be eligible for your club, you needed to be a student at Fort LaBeouf, and you needed to be female. You needed to be a student at Fort LaBeouf and female. Think about what that would mean, compared to what it would mean if, in order to be eligible to be a member of the club, you needed to be a student at Fort LaBeouf or female, like either or. So, it's the same thing with these compound inequalities, but we'll get to that in a second. But for right now, here's what you essentially do. Here we have two separate inequalities. We're just going to solve them separately. And that would be negative 27. And then to finish solving for x, we would divide both sides by 3 and end up with x is greater than or equal to negative 9. Over here, it looks like we end up with x is less than 6. And again, the word the whole time is and. And so imagine all of the solutions, all of the potential numbers that are greater than -9 and less than 6. What kinds of numbers are greater than -9 and at the same time less than 6? Doesn't that mean basically in between -9 and 6? Because, this graph greater than, -9 and, less than 6, these graphs are going to basically collide with each other. And just let them collide, and the final answer, because you want what's on this graph and what's on this graph. Just one more quick little elaboration here. This graph of x is less than 6, watch. Technically, this graph on its own keeps going to the left forever, including numbers like -10, -11, -100, -100,000. But our final graph needs to be only numbers that are not just less than 6, but they are, and greater than -9. And so the final graph ends up being everything in between those two numbers. The graphs collide with each other, which usually happens with the and compound inequalities. Now this one's an or, but same deal, we're going to solve them separately for y here. It doesn't matter what the variable is. So this one we end up with the variable y is greater than or equal to 4. Over here, again, we only flip the symbol when we find ourselves multiplying both sides by something negative or dividing both sides by something negative. Like here, we're just dividing both sides by 3, so we're going to leave it as less than or equal to. And so this was an or. So we have to be greater than or equal to 4 or less than or equal to -3. Like either one. As long as you're greater than or equal to 4, you're good. You're a part of the final solution. Or you could be less than or equal to -3. So essentially, we're going to keep every solution to this guy, and we're also going to keep because it's either or. You could be on this graph, you could live on this graph, or you could live on that graph, as long as it's one or the other, right? That's the way the word or works. So we have greater than or equal to 4, or less than or equal to -3. And this is the way or graphs for compound inequalities. This is how these graphs are usually going to look. Graphs that are running away from each other, and we're going to keep everything about both graphs. The greater than or equal to 4 or the less than or equal to -3. And that's the final answer to this example. And that's where we're going to stop for now. There's going to be like other activities that kind of like further the conversation, and we're going to do more types of crazy examples, but just kind of like a foreshadowing in case you're watching this video, I guess. The norm, right? The norm is that and graphs will end up looking like this. And or graphs will usually, not always, we're going to investigate that kind of stuff in activities, but or graphs will usually end up looking like this.